Okay. Hello? Hello? Can people in the back hear me? A little bit? How about this? Hello? Hey, Nathan? Can you hear me in the back? Okay, good. Okay, we should get started. Okay, take a seat. In our last lecture, we basically finished up mole balance, and basically mole balance, what we need to remember is this equation and the differential form of this equation. So what mole balance says is that in the system we are studying, once we draw a control volume, and the amount of accumulation in that control volume, the species that's been accumulated in that control volume, basically equals to two sources. One is net flow going into that control volume. The second is production, if we have a reaction that's generating the species I. Okay, so in this equation, in order to compute the net flow into the control volume, basically what we did is we basically we take an integral of the molar flux of species I all over the surface of the control volume, right? So in today's lecture, we're going to talk about how we can, and we talk about, like, for the molar flux, there are two sources. One is like molar flux is due to the bulk fluid motion, that's due to advection. Then there's also a part of the net flow comes from the molecular diffusion of species. Okay, so we're going to talk about that in today's lecture. So basically, we're going to introduce Fick's law, and we're going to discuss molar fluxes in a binary system. So let's look at the molecular origin of diffusion first. So, sorry. So on the right, we have two kind of like schematic showing two type of fluids. One gas, on the right you have a gas, and on the right you have a liquid. So basically any type of fluids, fundamentally they are made of like molecules, right? And the difference between gas and liquid usually is that gas has much lower density, which means in the same volume you have less amount of gas molecules in the same volume compared to the liquid case. Okay, so because we know, as long as we are not at absolute zero temperature, then the molecule will have some type of thermal energy, right? And because of this thermal energy, they will kind of move in the space. For example, like on the left, we have this red particle. It can move in, this direction, or this direction, or that direction. Okay. Now, this motion cannot just happen forever, because it's just like you playing, the pool. The molecule is like a ball. When it moves around, there's a chance the molecule will collide with another molecule nearby, right? And this collision will basically change the trajectory of both of these two molecules, right? And we call like the distance one molecule can travel before it hits another molecule and change its trajectory. We call this path to be a mean-free path, meaning is average distance of the molecule can travel before it changes direction, changes trajectory. Okay, Now, obviously, in liquids, we have more in the same volume, we have more molecules. So there's a higher chance of liquid molecule to be engaged in a collision and change its direction of movement. So in liquid, the mean free path for liquid molecule is going to be smaller than in the gas situation. Okay, because of this, possible collision when molecule move around. So we cannot really predict its actual, moving pathway. So that's why this motion, this kind of phenomena is also called random walk. Okay, and there's a theory called random walk theory just to explain this type of phenomenon. So then, if we look at, in this case, we are looking at almost like a pure phase. But what if we look at an example where we have, two components in the system? Let's say in this example, right, we have species A on the left, and we have species B on the right, right? So initially, they are kind of like separated by a wall or something, right? And this can be then at some point you just take out this wall, right? Before you take out this wall, there's no way that species A can go to the right and the species B can go to the left, right? And I mean this is like when you cook, right? You open the cap of a vinegar, right? At that point, the vinegar molecule is going to start to coming out from the bottle. And meanwhile, gas molecule, air molecules start to go into, your bottle, right? This is like that. So now, at some point, we remove this wall, then all of a sudden, it becomes possible for a molecule of species A move to the right, and it becomes possible for the species of molecule of species B move to the left. Okay. Now, obviously, we can tell that there are more molecule A on the left than on the right, right? So which means there's a higher chance for molecule A move to the right than for molecule A move from the left, right? And that is equivalent to say over time we're going to see molecule A move to the right, right? That will cause the number of molecule A in the left chamber decrease, right? By the same token, we can see, over time, we will see the number of molecule B on the left will decrease, right? So which means we have created a gradient in concentration at when the moment we take out this wall. But as time goes by, this random walk of molecules, they will smooth out this concentration and then eventually homogenize this mixture. Okay, and the same thing will happen for a liquid mixture. Yes, Nathan.
So I'm just a little bit confused on that. It seems like the molecules would diffuse from high concentration to low concentration because of their random movements, and there's like nothing in front of them to keep moving into the concentration area before like they bounce back, right? That's how it works. So if there's just a different kind of molecule in the other area, but it's still low concentration of A, like why would they move to the second region if there's still like other molecules there that could bounce back to A? Does that make sense?
So it all has to do with, all has to do has like concentration. Higher concentration means you have a higher chance of moving, right? In this case, on the left, we have higher concentration of A. That means the possibility of molecule A move to the right is higher than the possibility of molecule A move from the right to the left, because you just don't have as many molecule A on the left, on the right, right? So then you don't have an equal amount of flux in both ways. You have a higher flux moving from left to right. You have a small flux moving from right to left. That will create an imbalance. and net result of this imbalance is that, you know, net result would be that kind of like overall you have species A moving from left to right. But in fact, there will be some fundamentally at molecular level, there could be some molecule A move from, you know, right to left, right? It's just like at the single molecular level, you have both. You have motion in both ways. But if you look at the system at the continuum scale, at the connectively, right? Then you have a net movement of species A to B, right? It's just like, let's see, you know, after a movie is down, right? You go watch a movie with your friends. When the movie is down, everybody's leaving the room, right? But maybe your friend just forgot about his, you know, his phone. Your friend just go back to get this, you know, his phone. But in this case, even though at an individual case, there's a still chance people can go back to the movie theater to, you know, do something to, but the kind of the connectively, people are leaving the room, right? Does this make sense? Okay, great. So then at continuum scale, right? Continuous scale means that now we zoom out, we don't look at individual molecule, right? Because there are so many of them, and it doesn't make sense for us to track. First, it's impossible, and secondly, it doesn't make sense for us to look at every one of them. So we care more about what the molecule to do in a connective measure, connective, you know, way. So then we zoom out, and at the continuum scale means that we look at the picture at a scale that's much larger than the, you know, the main free path, the length of the main free path. Okay, so then we call this random walk phenomenon at a continuum scale as diffusion, right? Then we know that in concentration gradient will drive the diffusion, and diffusivity is a kind of parameter we define to describe how fast diffusion can happen. And we know that diffusivity, well, is dependent on the main free path, right? Because we talk about this. The longer the main free path, that means one molecule can travel a longer distance without being, you know, without being engaged in a collision and changing its direction of movement. Okay, so which means that I mean that the longer the main free path, we have a higher diffusivity, right? So as a result, gas will, you know, gas would typically have a higher diffusivity than liquids. So and at the continuum scale, how do we describe this homogenized process, right? In this case, we have initially we have two separated species, and at the moment when we take out the wall, they start to mix, and then we have a you know, flux of A moving to the right and flux of B moving to the left. So how do we describe this flux or this movement, connective movement, at a continuum scale, right? We can define an average velocity, you know, U as a function of space and time to describe the connective connective movement. Then this average velocity is kind of like the average velocity for all individual molecules or individual particles. And there are several ways to compute the mixture velocity. One is we can do a number average. That is to say that, I mean, for example, in a mixture, if we have n different species, if we want to compute the average velocity of all these, you know, species, what we do is that, or not n different species. Let's say we have in following the previous example, right? So for species A, there are so many different particles, but they're moving in different velocity, right? Let's say we can track all of the velocity. So then we can count how many particles are moving at one particular velocity, right? Then the number average velocity says, first we can compute the total amount of total number of particles, right? Which is very simple. You just sum individual number of particles, you know, all over the n possible scenarios. Then on the top, if we know if there are like n different velocities, and if we know the number of particles moving at a particular velocity ui, then we can just sum them together. So that will give us a number averaged of velocity, right? So at the continuum scale, I mean, we can do this. Well, so this give us the total number of species, and we know that this. Oh, so this can be converted to this, where xi just give us the molar fraction of you know, species I. Okay, so that tells us the molar averaged velocity. So then we can write down, and we know that for any individual particle, its velocity is not necessarily to be the same as the molar average velocity, right? So then we can write down an equation to describe such a difference, right? For any individual particle, we can write down its velocity to be ui, and it's going to be a summation of the molar average. This is supposed to be capital M. Molar average velocity plus a difference. And this difference is basically the velocity of species I relative to the molar average velocity, okay? So just conceptually, we can do this. So, and remember that this molar average velocity is basically like an artificial average we create to help us to understand how do all the particles move in a connective way, right? And in this, I mean, we can also do a mass average, right? Because I mean, if the mixture is made of only one, if the system is made of only one species, so then all the particles have the same kind of like mass, molar mass. So we can just use the first method. But what if we are dealing with a mixture? There are many different, you know, species with different molecular weight. Then we cannot simply count the weight. We cannot simply count their numbers because the weight are different. So in this case, we can do a mass average. So similarly, you can compute the total mass. Then we can weight the velocity of species I by its weight. Okay, then do this at continuum scale, and this will this equation just reduced to this, where omega is the weight fraction. Okay. Similarly, here we can also write down this equation. So the velocity of one particle I can be break down into two parts, right? It can be a summation of the mass average velocity plus the difference, and this difference is the velocity of I relative to the mass average velocity, right? So in other words, the definition of VI diff is ui minus v, right? So this is the actual velocity of species I, and this is the mass average velocity, right? Okay. Now we have a concept about how to compute average velocity for a mixture. We can move on to talk about molar flux in a binary system. So here we only consider 1D scenario, so we can write on all the vectors into scalar form. So I mean, in the previous example, we have a mixing problem of two species A and B, and we know that there's a flux of species A moving from left to right. And how do we describe that molar flux? So here, the molar flux of species A is basically can be computed by, if we know its velocity, right? We can just multiply its velocity with its concentration, okay? Then Ca, the concentration is A is the total concentration multiplied by the molar, molar fraction of A, right? So Ca equals C multiplied by Xa. Okay. And I mean, by rearrange this equation, we should be able to compute, right? If we know the molar flux of A and concentration of A, we can compute the velocity of A by dividing, right? So if you rearrange this equation, moving Ca to the left, so we will be able to get this equation where basically the velocity of A is basically the ratio between the molar flux of A divided by its concentration, right? Now, let's drill down this further. Just like what we did with the velocity, right? So we call that VA. We can write VA. This is the velocity of species A to be two components. One is the average velocity of the fluid plus a difference, right? Difference. By the same token, we can write down molar flux in a similar format. So we decompose the molar flux of A into component. One is due to the average motion of the fluid, right? So it's going to be Ca multiplied by Vm, right? Plus the difference. So then the next component is the so-called convective flux. So it's a molar flux of species A due to the motion, bulk motion of the fluid, right? Because the fluid is moving, is flowing around. Then this is due to, and the second part is the so-called diffusive flux. So, and it has nothing to do with the bulk motion of the fluid. Instead, it only has to do with the relative motion of species A to the bulk motion of the fluid, right? So so I mean we can do a simple example here, right? So in our control volume, let's see, this is our control volume, and we can pick a very small, I mean volume, like differential volume. For example, this is a dV. Okay, and let's say if the fluid at this point is moving at this, direction, right? And we know at this particular point, the concentration is C, right? And obviously we know that at this crossing this, crossing this plane, let me draw a imaginary plane here. Sorry. Okay, let me do this. Let me just transfer the example below, right? So crossing this plane, there will be a molar flux of A that is purely due to the motion of the fluid, right? Because the fluid is flowing through this point, carrying carrying species A with a concentration of Ca. So it's going to create a molar flux. That is molar flux that is Ca multiplied by Vm. Okay, but meanwhile, let's say if the concentration of A in this control volume is not uniform, which we can expect, there will be a concentration difference at this point compared to the nearby point, right? Which means then because of this concentration gradient, then there will be some some molecule of species A doing random walk, through this plane. That's going to create another flux, J, we call it diffusive flux, okay? So, and then you add them together, that'll give you the total amount of flux, okay? So, some more equations here. So, the difference the so-called diffusive velocity is the velocity that is related to diffusive flux, right? So we cannot really measure the diffusive velocity, but conceptually, because we know the diffusive velocity contributes to the diffusive flux, that's how we can just compute the diffusive velocity by dividing the diffusive flux with the concentration A, right? And that should be, by definition, the difference between the fluid difference between the total velocity of species A minus the fluid average velocity M, Vm. And total molar flux, right? We are dealing with a binary mixture. So at any point in the control volume, we have the flux of A, we also have flux of B. And we can definitely compute the total molar flux of A plus B, right? That's by definition NA plus NB. And then by definition, we should also have the molar average velocity should be the ratio between the total molar flux divided by the concentration, right? Because I mean here, if you look at this equation, we can just write the same for the total, right? So we have NA equals VA multiplied by CA. We should also have NB equals VB multiplied by CB, and total flux equals V plus C. Okay, and this is all by definition, right? So now, then you could just rearrange this equation. You get this one. So this is there. Okay, you get this one. And if now if we break down total flux to be NA plus NB, right? Then if we divide NA by C, right? C can be so NA is because NA is VA multiplied by CA, right? Now, if we plug this there, then CA divided by C, that gives us XA, right? Then XA multiplied by VA. That's how you can break down this equation. Okay, let's see. Okay, so I'm gonna keep the notes here, but I'm gonna write down the diffusive flux always sum to 0 somewhere. So now I'm going to derive the diffusive flux is going to be sum to 0. So I'm going to prove that here. So let's do this. So let's just take like a binary system as an example to do this. So it's kind of much simpler. Now let's look at this. The total flux N equals NA plus NB. And we know NA can be written as this, right? So similar NB can be written in a similar format. Now, if we further break down this and we just put all the similar terms together, so this can be XA plus XB multiplied by N plus JA plus JB. Okay. Right. So I'm just adding the convective flux of A into one term and the diffusive A and B and diffusive flux of A and B into one term. Right. Now XA plus XB for a binary system that is that is 1. Right? For binary system, XA plus XB is 1. Now then you have N on the left and on the left, you can just cross them out, right? So that just means JA plus JB equals 0. Okay, which is to say, in a mixture, the diffusive flux for all the species, you add then if you add them together, they should be 0, right? For a binary system, diffusive flux of A plus diffusive flux of B equals 0, right? So physically, what does this mean? This means that recall our example about the mixing of species A with B. This means that whenever you have diffusive flux of A going in this direction, there will be diffusive flux of B going in the opposite direction with the same magnitude. Okay, so mathematically, you add them together, they cancel each other, right? Okay, now we can introduce Fick's law. So so here, from this, if we rewrite, right? If we rewrite the molar diffusive flux of A on the left, right? We move this molar convective flux to the left. That will give us this equation. And from this equation, what we can tell is actually the molar diffusive flux is the kind of like is like first of all, it's the difference of total flux between and the molar convective flux, right? And this diffusive flux are only defined relative this convective and the total flux. Okay. Now we can introduce a Fick's law that says for the diffusive flux, basically, it is proportional to the total concentration, the diffusivity, as well as the gradient of the molar fraction of A, right? So, this is like similar to a Ohm's law in which you have current, right, or current density to be proportional to conductivity multiplied by the gradient of electric potential, right? So, and fundamentally, these two equations are actually the same because Ohm's law just tells us the flux of electric charge, right? Because current density is basically the flux of electric charge through a certain plane, and it is proportional to the conductivity and the gradient of electric field. So the electric field is the driving force to drive charge to move, and the conductivity is basically the conductivity. So what we can see here is by this entity, we can interpret it as the grad XA, the gradient of the molar fraction of A, to be the driving force to drive this mass flux, diffusive flux of A, and the diffusivity is basically the conductivity, right? So the higher diffusivity you have, the easier for species A to diffuse. Okay. And DAB is the same as DBA. Why is that? And we've proved JA to be minus JB, right? In last slide. So why DAB equals DBA? The diffusivity of A in B is the same as the diffusivity of B in A. Why is that? Anyone have a clue?
Same. Even if A is like moving at B, the B is still like, even if it's station.
Yes. So conceptually, you can treat it that way, but we can prove this mathematically. If you start from JA equals minus JB, right? If you write down the equation for both of them, you have minus, say, DAB grad XA equals minus, say, DBA grad XB, right? And we know that XA equals 1 minus XB. right? And then we can cross out some common terms, right? We leave the minus sign, we leave the C, and then these tell us gradient of XA is the minus of gradient of XB, right? Right, and you just plug in everything. Then you have, oh, sorry, there's a minus sign here, which I missed. So this should be positive, right? Because there's a minus sign here, right? So let's do this. So DAB grad XA. Let's keep the minus sign here. Then, because we have a minus sign here, that give us minus DBA XA. Right? So then, sorry, grad X. Then DAB equals D. Right? So mathematically, you can just prove it. So that just means basically, in a binary mixture, the kind of the mean free path of A is the same as mean free path of B, or the speed of A moving in B is the same as speed of B moving in A, right? So then we can, in 1D case, we can simplify the equation. We can use derivative to replace gradient, right? So if we only consider about one dimension, and let's say in this dimension we use Z to describe the location of this dimension, we can just reduce grad XA to dXA dZ. Now we can just rewrite the total molar flux equation by plugging in the Fick's law for the total flux of A, right? So we have the convective molar flux that is proportional to the the A's molar fraction and the molar average velocity of the fluid minus the diffusive flux, which is proportional to the diffusivity and the kind of the concentration. I mean the derivative of the concentration, or the molar fraction. Okay. Similarly, we can do this for B. Then for steady state diffusion in binary system, just we can write down the flux. So then the total flux of A can be written as the molar fraction of A multiplied by NA, total flux N. Right. This give us the convective convective molar flux plus diffusive molar flux. And we can also compute the flow rate, right? So basically flow rate is just flux multiplied by the cross-sectional areas. Okay. And if there's no bulk flow, then, right, if there's no bulk flow, we know Vm equals 0, right? There's no advection, then the total flux NA is only equals to JA, right? Remember, NA refers to the total molar flux, J refers to diffusive molar flux. Now, if there's no bulk flow, then the total molar flux is just equal to the diffusive flux, right? And further, if we make the assumption if C is constant, if C is constant, C does not dependent on location, then we can move C into the derivative, right? You can only do that when C is a constant, right? Then if you do that, that gives us the CXA easy, right? So then CXA is just C, okay? So lastly, let's look at two examples, right? How we can compute the diffusive flux. I mean, three examples actually. For a planar system, for a concentric cylinder system and a spherical shell system. For the planar system, this is kind of the simplest case. We can just use this equation to compute the total molar flux, right? When there's no bulk flow present, right? And for example, let's say if this is a membrane, and we talked about membrane-based separation previously, right? And for membrane-based separation, typically you have some species who have different concentration on both sides of the membrane, right? It can be salt, right? And then that's the case for desalination. We have one side, we have potable water. On the other side, we have the salty water, can be brine, can be seawater. So then in that scenario, A here would be the salt or ion. Then we have a different concentration of species A on both sides of the membrane. How do we compute the diffusive flux? We can just plug in everything into this equation, right? Here, we can approximate the derivative by difference, right? We can just simplify dCA over dZ to be, because we don't know what the concentration profile in this membrane, but what we can do is we can do an approximation, use difference of Ca to approximate derivative. Okay. Then across the membrane, the difference of concentration A would be Ca2 minus Ca1. And there's distance between these two concentrations at the two ends of the membrane would be the thickness of the membrane, which is Z2 minus Z1. Okay, so that will give us this is this term. Then this multiplied with the diffusivity give us the flux of A throughout the membrane. Okay, for the concentric cylinder case, note here in cylindrical of spherical coordinate, constant molar flow rate does not imply constant molar flux, right? So instead of using flux, here we use flow rate. You can solve this equation similarly in cylindrical or spherical coordinate. We will get the molar flow rate in this case to be dependent on the log of the ratio of R2 to R1. Okay. Yes.
Is no bulk flow, does that just mean it's at steady state, or does that mean that there's no inlet or outlet? What do you mean by no bulk flow?
Low bulk flow means basically the velocity. I mean the average velocity of all the species are zero. There's no flow.
Okay.
Right. So there's no, for gas, there's no wind. For liquid, there's no, it doesn't, steady state is a different concept. Steady state, so steady state means the quantity of the value of a parameter does not change with time, right? That's the definition of steady state, which means, I mean, for concentration, steady state means dC dt equals 0. That's steady state. Okay. But steady state doesn't mean you don't have flux. There could still be flux, right? It's just like the flux does not change the concentration profile over time. Okay, makes sense?
Yeah.
So so lastly, we're gonna just add, review the molar balance equation again. So what we do here is just like change the molar flux term by what we just learned today, right? Just replace the molar flux term by this equation where we replace the total molar flux by the convective molar flux plus the diffusive molar flux, right? In this way, we can just modify this integral form and differential form of the mass balance. You have, right, for example, here, if you replace Ni with it, with that, you have a net flow caused, not net flow term caused by convection. You have a net flow term caused by diffusion. Okay. Okay, we're gonna stop here today, and next Monday, we're gonna talk about some examples.